Hey, it's been like a year and a bit. I don't know. Um, I just wanted to chat about some cool stuff that I've been doing and mostly, explain some ideas without so much effort. So this is gonna be pretty much just me while streaming, playing around. Today we're gonna be playing around with the concept of like how could you use types to track the size of stuff and to make it faster. This is kind of like the language. Feel free to pause and try to understand what is going on. The main question that I'm going to be trying to ask today is what is the size of something? And the size here I mean in the sense of like how much memory does it uses. For functions, I'm going to be ignoring because it's actually does not matter. It's way easier and you can reduce functions to pairs and whatnot. So the question is going to be about pairs. And pairs is kind of the general case, so it more or less does work. An initial example of this is that we can say that the size of the booleans is 1. So here I'm going to be using bytes instead of words. But you should really not think about this in terms of bytes, words, or something. You should just think about it as the size of the boolean. So what if we have something like 4, which is a boolean, and another boolean? So it's 2 booleans. What is the size of this? Well, you could argue that the size of a pair should be the size of its components. So a good way of saying it is that the size of it should be something like this. And then if this is, this should be the size of A plus the size of B, which means that the size of 4 should be the size of the boolean plus the size of the boolean. This is cool. It does not work in any sort of general case. Just to, the reason why we're tracking this on types is because it's generally a good place to do it. You could track it in some other ways, but you're gonna see that if you play enough, all the problems that you have for types are gonna also happen for kinds, or even if you try to hack it on the term level. It's a very general problem. So for this one, it does work, right? So the size of this should be pretty much 2. The next problem is, what if this is not a simple type? So this in general works for any for what we call simple types. For any type that is not dependent, a good one is, what is the type of this? So X is a type and this is X. Another way of saying it is something like this. If you go here and you try to enter using the same technique, you're gonna see that it does not work. Now we have the size of type. I forgot to add it here. So, the type of all types. Universe. And it goes here and here. So first, what is the size of type? Well, the type should only exist on the type level. So a good one would be to say that the size of the type is 0. That's cool. Now, what is the size of A? Well, the size of A depends on what A is. But the general problem here is you don't know the size of A. And this also shows up for some other examples. You can use dependent pairs and booleans to make most of the ADTs. So a good one is, let's say you wanted to do either. A traditional way of doing it is something like, I do tag, and here's going to be the case. It's just going to be a type. And if it is true, if the tag is true, it's going to be A. Otherwise, the tag, it's going to be false. So what is the size of something like either of bool? And let's go, the size of bool or bool. In this one, it's trivial because it's either both of them, right? So you can see here that is going to be the size of the tag. And because this is Boolean, it's either going to be a Boolean or a Boolean. But now let's say that we put any other stuff here. I'm going to say that, let's say we say either bool or 4. Remember, 4 was this type. It has 4 options. The size is 2. What is the problem now? You don't know the size, not without looking at the tag. So the problem here is you cannot do an operation like size of in a language that has polymorphic enough types So if you have like dependent pairs or dependent types in general, or even weaker stuff like the system F or system F omega, you just cannot know the size statically. So you cannot do this based on the type. And this is one of the main reasons why languages like something like OCaml, they do not have unboxing by default. It's because if you want to have very ergonomic polymorphism, this simply does not work with like unboxed types. Unboxed types being a type where like you can actually put stuff together in memory, so it's laid flat. So a good example, if you had unboxing at this one, and let's say this one. So like, what would be the size of this? If you have unboxing, this is just the size of all the node elements. So this would be a size 4. If you have this being boxed, well, it's going to be way, way different. At least something like this would need to be like 2 words, which would be like 16 bytes. It's probably actually more than that, but you know, the general problem is if you have unboxing, everything is laid flat in memory. You get a lot more performance. You do lose a thing called sharing. And I'm going to show an example later using linked list on why this matters so much. But here is part of the problem. If you do have slightly more polymorphism, you don't know the size of stuff. And because you don't know the size of stuff, it cannot be unboxed. If you go and you check this in something like Rust, you can see that in Rust, an ADT, if you're doing bool or for, this is always going to have a single size, which is going to be the size of the biggest case. So if you try to do something like left of boolean and right of for, well, we need at least a byte for the tag, which here it's a word. And so this is going to be 2 and this one is going to be 5. So it would be at least 5 words, 5 bytes. Likely this is going to be round up to 8. So the size of t would be 8. And this is enough because at the worst case scenario, the size of t is actually 8. And keep in mind, again, counting bytes, it's not about bytes. So what is a good solution? What is the answer for the size of this? Oh, the answer for the size of this is that we need to actually change this. We need to change the size function for pairs. The size function for pairs originally was size of A plus the size of B. It cannot be that. And a good way of seeing it is because B is dependent. B is a function. So what should be the size of this? Well, the size function now needs to be a dependent size function. And here, what we're going to be asking is, what is the size of an object, like a variable, an actual pair? We just know that this object, we're calling it M, this object has this type. And so now we can do something. And the nice thing that we can do is that we can say, hey, it's the size of A, this is still the same stuff, plus not the size of B, the size of B applied to the first element of M. And this actually makes some sense let's play with the example of the exist. So let's say that I had an M, which is an exist. We know that exist is this. What is the size of M? Well, I know that the size of M is going to be the size of type, which we're saying here that it's 0. It could be anything, it doesn't matter. But now the size of this is the size of FST of M. If we say that this is 0, you can go here and, we know that this is, the B function is going to be A, so this is going to be the size of this, and this is going to be the size of this. It's the size of SND. This is actually wrong, by the way. I just made a mistake. Because this is dependent, this should be the size of FST of M. And this should be the size of SND of M, which is this. And now you can actually go and see, well, this is the size of FST of M. It doesn't matter what the type is. We know that the type is going to be size, not going to have a size. And now we're checking the size of SND of M, which is just FST of M, because that's just A. If you think about this, as a function, this was pretty much this function. So this, the b of this, and that's why like, it's actually this, where this is the FST of m, which just reduces to FST of m. Now, what is the size of m now? Well, I know that this one is going to be 0, so I really don't care, which means the size of m is equal to this. What is this SND of m? Do I know it? And the answer is, for this case, there is no way we actually do get stuck here, because we don't know what FST of m is. And because we don't know what FST of m is, we cannot compute the size. But now let's say we do have dependent types. So I had a function like this. The function was taking this. And for some reason, I'm trying to figure out the size. There is actually a lot of reasons you do need the size very often. Can I introduce something else that gives me more information? Actually, I can. For example, I could say that, well, the FST of m, of x, so like this a right here, we could say that this a right here is equal to bool. And now remember, the size, if I'm trying to find the size of x in this context, which I'm just going to say it like this. So now I do have a hypothesis that this x is a pair, and I do know that this is a Boolean. Well, if I try to do this, again, it's going to reduce to pretty much this. But now we do know some stuff. Now we do know by h, by looking at the quality that the user is providing to us, I know that this is going to be equals to bool. And what is the answer for the size of the Boolean? It's 1. So in a very composable way, I was able to arrive that the size of x should be 1. And this does work for any cases. I want you to keep in mind that the main thing that we're saying is that whenever you're trying to ask for the size of something, and ask for the size of something is just a size function, we're computing the size of something, we may actually need to look at the value. And this is very important. If you look at this, and again, for any m that is a Boolean, I'm going to say this. Now let's look at the either case. Remember, the either case was something like this. So now let's say that I do have an either that is, either bool or for. So I'm going to call this E. What is the size of E? Well, either is bool or for. Here I can go and say, and just expand this to be like the FST of E, which is, sorry, I need to actually expand it because otherwise it's going to be hard to visualize that. So we know that E is this. And so what is the size of E? Well, the FST of E, here it's going to be a Boolean, plus the size of SND of E, which we know it's going to be this, where this tag was replaced by the FST of E. What is the size of the Boolean? Well, this one is trivial. We just say it's 1, right? So this is 1. Oh, now the question is, what is the size of the rest? And the answer here is that the size of the rest depends on which Boolean it is. If this is true, it's going to be something. If it is false, it's going to be something else. So I do not have, like, the answer to this. It's actually pretty much this, okay? Notice that this is not a final number. This is just an expression. But I do know that the size of E is this. Now, let's say I'm doing, I'm actually looking at the Boolean, and for some reason I did case analysis on FST of E. And so here it's when it's true, and here it's when it's false. Inside of this second expression, what is the size of E? Well, I know that here, in this position, a good one that I can have is that the FST of E is equal to true. And so I know that here, if the FST of E is equal to true, we can go here and we can just compute the FST of E is equal to true, which if it is true, it's going to reduce to 4, which to bool, which means this is bool. And if it is false, it's going to be 4. So this is false, and we go to 4. So first, notice that the size is dependent. The size is either 2 or it's either 3. So if the FST of E, here it's when FST of E is equal to true, and here it's when S and D FST of E is equal to false. So the size of E is either 2 or 3. The nice thing is I can actually compute it and I can actually manage it. But if you give me an either, the either may be the simpler one that you want. Like, you don't need to round it up to 3. You could. Rounding up to 3 actually does work for some stuff. But the nice thing here is that we don't need to add any padding. And in this general solution, we can actually start to reason about some more complex types. Here, it just does not allow you to do a lot of stuff. But I want to give you an example of something that is that is a bit more useful. And here I'm going to be playing with a linked list. So we're saying, hey, a linked list is a recursive type, it's type to type, something like this. The traditional definition of a linked list, it says that we have a tag. The tag says that it's a new, pretty much. And the tag is a boolean. If the tag is true, this is just the empty unit, the empty pair, which we do have some ways of doing it, but let's assume that we do have an empty pair. If it is not that, it's going to be the first element, which is A, and the tail, which is going to be a list of A. This is the case. If this is unboxed, there is no problem. If this is boxed, sorry, there is no problem. Given that this is a list, we can look at the tag and we know if it is the final or not. A very natural function to implement for lists is what we call fold. And here I'm already using whatever syntax I want. So I apologize. I hope you guys can figure out from the syntax. And this is the accumulator, the element. So we have A and B. The initial is, I'm gonna call it B. The accumulator is B. The head is A, and we return B. And this at the end we return B. So how do we define the fold function? The fold function is defined recursively, something like this. Now we're going to be looking at the tag of the L. So I can actually kind of extract like this. So you can see the payload, and here I'm going to do L. And what I'm going to be checking is if the tag is true or not. If the tag is true, well, we know that then it's the empty of the list is empty. A good one would be maybe to call this is empty. There's a reason why I was calling tag. I'm going to go back later. And so, okay, now we have the is empty. If it is empty, we just return the unit in it, so the initial value, because we know that the payload here is going to be nothing. So I can actually just go and do this for the payload. It's actually gonna work. What if I actually go? What if it is not empty? Well, then we have the list, the tail, and here we have head and tail. Yeah, it's going to be on the payload. And so here I'm actually going to recurse. So my thing is going to be fold of L. The initial, now it's going to be F of initial and head. So like how it should. And here I recurse on this. So this is pretty much a very standard definition of fold. It's not super ergonomic. It's not super nice. But the nice thing is this 100% works if it is if this is boxed. I want to give you an overview of how could we make this boxed. And for this, I'm actually going to change the syntax a bit, just to make it easier to reason. So this is when is empty. I'm going to use a almost TypeScript-like syntax. So this is when it's empty, and so this is just empty. And when it's empty, it's false. It gives you this. Notice that those two types are the same. They are just the same. Here is empty. Here is empty was it was a pair, and here it's where you have a tag, and if the tag is one, otherwise it's the other. But notice that if the tag was true, this was a pair with the tag plus this. If the tag was false, it was the second one. So it's actually the same. In fact, normally we would normalize this one to that one. The nice thing about this one is that it's kind of nicer to see that if you change the tag, let's use something like TypeScript, where this would be an empty tag. And here it would be what we call cons, so new and cons. Now let's say this was unboxed. What is the problem? Again, the type of the list is not known statically. Well, you could say, but the list is a list of booleans. What is the size of the list? It really depends, because this becomes flat. So for example, something like true, cons, it's going to be true, and then it's going to be cons, false, and then it's going to be the empty one. This one has the same memory representation as this. So you can see that to know the size of it, here I need to do an empty. Yeah. You can see that to know the size of something, you actually need to actually know the tag. If this is empty, sorry, I'm using null, right? If this is null, then it's just a tag, which it depends on the size of the tag and whatnot. The nice thing about this is that this is actually way faster. Because if you're trying to look at the next element, you don't need to do like a pointer jump. So if we make this in the traditional way, this would actually be something like, I'm gonna call this B, and we have A, and we have, so this is B, this is A, this is C, this is A. And we have A here. And so this was something like this. Notice that to actually go and visit all the nodes, you need to, like, first you read the tag, then you read the payload, then you go to the next one. So you jump from B to here. And if you think about this as being memory, those components could be in any place. The nice insight here is that if you make these unboxed, we know that they are actually one after the other. So we know that everything here is laid flat like this. And so C and this have the same memory layout, which is good. This is very, very good for performance. We have a problem. We lose sharing. What is the main operation on a linked list? We have a thing called cons, which takes the list, the element. So here it's list of A. And we put it together by doing cons of L, head and L. We call this the L. This operation, like the main advantage of a linked list is that this operation is O1. But if this must be flat, we have a problem. Because now you would need to copy the whole tail. And I'm not even going to get into how could you copy it. You could copy it by, checking stuff. But the interesting thing is, if you only have the unboxed linked list, this is not O1. This is ON on the size of the list, at least ON. So we have something. We need to do something. What is a good solution? We can add a third node where we call this just a box list. And so whenever you want to make, cons in a O1 way, you can actually go here and you can actually say, hey, this is cons, and we can actually box the list. In fact, probably I would ask this list to be boxed. And this is like in Rust. But the main thing is that whenever you have something of type box, we know that this is a pointer, so we know it's going to be 8. So this is always an operation. This is always an O1 operation. But now it does give us optionality. So now we can choose, is your code going to be flat or is your code not going to be flat? It really depends. If I'm doing a map function, I should just make this flat. If I'm doing a fold, well, I need to now handle 3 cases, right? And I'm going to show for the map function because this provides you with like a major optimization. And this is actually something that would make most functional languages much faster. So imagine that I start with list of A. And I'm going to do a fold, and I'm going to map the element from A to B. I'm going to be doing a map. And at the end, I return list of B. Here, I'm going to be doing A and B, and L and F. What is the first thing that I need to do? I'm going to extract this into the tag and payload. I'm not trying to be very ergonomic here. And I'm going to actually do pattern matching. So please don't look too much to the syntax. And here it's going to be cons. and here it's going to be link. The nice thing about this is that, well, I know that the payload is just a list, so I just need to dereference the list. If this is link, I'm just going to do payload and f. Now, what if this is a cons? What if this is null? If this is null, I just return null and empty, not a problem. And if this is a cons, I'm going to return a cons of something, of course. But here I'm going to say that my tail, because first I need to split those, tag and tail. I can do this because if I know that the tag is cons, this is this. And here what I'm going to be doing is I'm going to map tail and f. I'm going to call head and tail. What is a really nice property about this operation? You're doing a map over a linked list. In general, this is a bad operation because whenever you're making a map over a linked list, you make like something really big at the end. And you're making all the intermediary nodes for no good reason and whatnot. And this by itself does not work because there is a transformation that needs to be done. Otherwise, this would not be ON. This would actually be like quadratic. But the nice thing that you can see here is that after I do a map, there is no more linked nodes. So if you imagine that this linked list, initially it could have like interactions on it. We call that a link. After doing a map, it does not have it. So after doing a map, traversing this is not very different from traversing an array. It's like it's laid flat in memory. As long as the size of A is constant, you can actually just go to the next element because you know that at the end of the day, this linked list is going to be 100% flat in memory. And so you may have heard in the past about like the cache locality of linked lists and whatnot. This actually does solve the problem. And by the way, this representation is not the best one. This is actually way suboptimal. A better one, there is like a better one that is something like this. That says elements, and here it's going to be an array of A. I think is this good? I think you could do this, right? Yeah, I think maybe this is better. Yeah, I think something like this. I don't remember. But the main idea is that like you can make a linked list way more efficient because after any operation that traverses the whole linked list, you pretty much have an array. And in fact, you can make it actually an array. So it's like that's why you need to play a bit. But this, for example, would say that the whole linked list at the end would be like a single cons and a single null. But this is still suboptimal. You can actually reduce the overhead a bit. And so that's kind of what I was trying to go through today, which is like, if you want to have unboxing and you want to have flexible unboxing with polymorphism, you cannot stop at the first step. Like you cannot stop and do what Rust is doing. You need to actually go the whole dependent type way because the problem of the size is actually the general one. As soon as you can solve the problem of the size, as soon as you can say, what is the size of something that is dependent? Then you can actually have dependent recursion, for example. And dependent recursion is something that you cannot do in Rust. I'm going to give some more examples that I'm thinking for, I'm making my own language. This is kind of well known. I've been making it for a long time. But a couple examples that I can actually do in what I call Teika. For example, this buffer. And here we have, this is not going to be like a Teika syntax. I'm just going to use something like that is Teika-like. And here I'm going to have an unboxed buffer. This is going to be pretty much an array. So the way that I do it is if this is 0, it's just an empty pair. If this is 1 plus n, well, we should call this the length, right? Just to make it like nicer.